Welcome back to the deep dive. It's amazing to think, isn't it, that time is something we all experience, but it can be so hard to grasp. I mean, we look at our watches, set deadlines, feel the pressure of it, but do we ever stop and really think about what time actually is?
That's a great point. We use it to plan, to remember, to imagine what's next, but defining it. That's where things get really interesting. And the way we've measured and understood it throughout history, well, that's evolved in some pretty incredible ways.
So for this deep dive, we're going to switch things up a bit. We thought, why not explore time with a quiz?
10 multiple choice questions. Just a fun way to look at everything from how we keep track of it to some of the really mind-bending concepts around time.
So are you ready to test your knowledge?
Let's dive in.
All right, first question. What is the SI base unit of time? Is it A, minute, B, hour, C, second, or D, day? Seems simple enough, right? But this gets at how we quantify time itself.
Yeah, those units we use every day, like a minute, 60 seconds. And did you know we sometimes even have to add what are called leap seconds?
These seconds.
Yeah, to keep our atomic clocks, which are incredibly precise, aligned with the Earth's rotation, which, as it turns out, isn't perfectly regular.
Ah, those tiny adjustments that keep everything running smoothly. And what about an hour?
60 minutes, of course, or 3,600 seconds if you're counting those. And then there's the day, usually 24 hours, but even the length of a solar day can vary a little.
So which of these is the most fundamental, the bedrock of how we measure time?
That would be the second. Second is the SI base unit, and it's defined in a very precise way. Since 1967, it's been all about the cesium atom.
Cesium atom.
Yeah, 1 second is the duration of, get this, 9,192,631,770 cycles of radiation from a specific transition in the cesium-133 atom. It's mind-bogglingly precise.
Wow, time measured at the atomic level.
Oh, yeah.
Okay, question 2. Let's go way back in time. Which ancient civilization is credited with the earliest known sundials that divided the day into smaller parts using a duodecimal system? That's base 12, by the way. Is it A, Romans, B, Egyptians, C, Greeks, or D, Mayans?
Taking it back to the early days of trying to track time, we've got some great civilizations to consider here. The Romans, for instance, gave us those crucial calendars.
Like the Julian and Gregorian calendars.
Exactly, which we still use today, although in a modified form.
And the Greeks, they were pretty innovative too, right?
Absolutely. The Greeks were masters of invention. Think Plato's water clock alarm.
A water clock alarm.
Yeah, around the 4th century BC. And later, Ctesibius made water clocks even more accurate.
What about the Maya? Their calendar system was really complex.
Oh, incredibly complex. The Mayans had calendars like the Hab, which was a 365-day solar calendar, and the Tzolk'in, a 260-day ritual calendar. But when it comes to the first to use sundials with that base 12 division, that was the Egyptians. The Egyptians, they were dividing daylight hours into segments using sundials, likely as far back as the 2nd millennium BC.
Wow. And why the number 12?
That's a great question. There are a few theories. The lunar cycle, the moon going through its phases, that's roughly 12 cycles a year. And some think it relates to observing 12 prominent constellations.
So that base 12 system from ancient Egypt, did it have a lasting impact?
Well, in a way, it might have indirectly influenced our modern 12-hour clock faces. And there's even evidence of even earlier timekeeping from the Egyptians. Obelisks used as gnomons, the part that casts the shadow on a sundial, that goes back to around 3500 BC. And a T-shaped time-measuring instrument from around 1500 BC.
Fascinating. Echoes of ancient Egypt ticking away in our modern world. All right, question 3. Time for a bit of wordplay. What was the atom in medieval writings referring to? Was it A, a fundamental particle, B, a unit of length, C, the smallest possible division of time, or D, a measure of weight? So we hear atom today and we think of the tiny building blocks of matter.
Right, the smallest units that make up everything around us. But in the medieval period, their scientific understanding was very different. The idea of atom as a unit of length or weight, not really a primary concept back then, at least not in relation to time.
So what do they mean by the atom of time?
Now, this is interesting. We have to go to the early 11th century. An English monk, Bertfurth of Ramsey, wrote a scientific text called the Enchiridion. He actually defined the atom as C, the smallest possible division of time. And get this, he even tried to calculate its duration.
You did?
Yeah, he determined it to be 1564 of a momentum. That's a very short period, about a minute and a half in modern terms. So his atom worked out to about 1594 of a second. And they even use this concept in calculating the date of Easter.
Wow, that's amazing. So the word atom, which now describes the tiniest bits of matter, once referred to the tiniest imaginable moment in time.
It really shows how language and our understanding of the universe evolved together.
Okay, on to question 4. Back to timekeeping devices. Which of these devices was known as the most precise timekeeping device of the ancient world? A. Sundial. B. Hourglass. C. Water clock, clepsydra. Or D. Incense stick. We've talked about sundials, but they had a major limitation.
Definitely. Sunlight dependent, no sun, no timekeeping. What about the hourglass?
With its steady stream of sand.
Hourglasses were definitely used in ancient times, especially important for navigation, measuring time at sea.
And incense sticks.
Incense sticks, candles, those were used in a lot of cultures to mark time, but often in a more symbolic way, not for precise measurement.
So which one was considered the most precise, especially for something like astronomical observations?
That would be the sea water clock, also called the clepsydra. And unlike the sundial, it could work day or night. They even found one in the tomb of the Egyptian pharaoh Amenhotep. Goes back to around 1500 BC.
That's pretty significant.
It suggests that they were very important, sophisticated even. The Greeks, the Chaldeans, they used water clocks extensively for astronomy, and Arab inventors later refined them even further. To be able to measure time regardless of daylight, that must have been revolutionary.
Absolutely, it must have opened up so many possibilities for scientific advancements.
A crucial tool for their time.
All right, question 5. A little history and revolution. The French Republican calendar, introduced during the French Revolution, divided the day into how many hours? A, 12, B, 24, C, 10, or D, 30.
The French Revolution, they wanted to change everything, create a new order, and that included time.
They weren't afraid to challenge the status quo. So 12 hours, that has ancient roots, maybe tied to lunar cycles, and 24 hours is the standard we use today. Option D, 30 hours. I don't think that fits with any historical systems.
You're on the right track. Think about the French Revolution's emphasis on reason and the decimal system.
Ah, so 10 hours.
Exactly. See, 10 hours. Each hour divided into 100 minutes, each minute into 100 seconds. A total break from the traditional base 12 system.
Wow, decimal time. But it didn't last, did it?
Nope. Abolished in 1806. It shows how deeply rooted our ways of measuring time are. Sometimes even logic can't overcome tradition.
Fascinating. Okay, question 6. Now we're getting into physics. Which of these is not one of the acknowledged arrows of time in physics? A, radiative arrow of time. B, gravitational arrow of time. C, entropic arrow of time. Or D, cosmological arrow of time. So the arrow of time, this is about why time seems to have a direction, why we remember the past, but not the future.
Yeah, it's a deep question. Even though many physics laws are time reversible,
So let's break these down.
the radiative arrow of time, that's about how waves spread out from a source. They don't converge back to it.
Like ripples in a pond.
Exactly. Then there's the entropic arrow of time, probably the most famous one. It comes from the second law of thermodynamics,
Which says?
that the total entropy, the disorder in a closed system, tends to increase over time. Things become more chaotic, not less.
Okay, and the cosmological arrow of time.
That points in the direction of the universe's expansion, from a very dense state after the Big Bang to the expanding universe we see today. So which one doesn't fit in this group?
Well, gravity obviously affects time, but is there a gravitational arrow of time?
Not really. It's B, gravitational arrow of time. Gravity warps space-time, leads to time dilation where time passes differently in strong gravity, but it's not seen as one of those fundamental arrows of time, not in the same way as the other three.
So gravity influences time, but it's not one of the primary reasons why time seems to flow in one direction.
Exactly.
Okay, question 7. Einstein time. According to Einstein's special theory of relativity, what happens to time intervals for events associated with objects in motion relative to an observer? A, they appear shorter. B, they appear longer. C, they remain the same. Or D, they fluctuate randomly. Now, Einstein's theory of relativity really shook things up when it came to understanding space and time. One of the big ideas is that the speed of light is constant for all observers.
No matter how fast you're moving, the speed of light doesn't change, which has some pretty wild consequences.
Yeah, mind-bending stuff. So how does this affect how we perceive time?
Well, option A, appearing shorter, that's actually length contraction. Things appear shorter in the direction of motion at high speeds. Option C, remaining the same, that's the old Newtonian view, time is absolute. But Einstein showed that's not how it works. And option D, fluctuating randomly, that's not how relativity works. Everything is very precise and predictable.
So if it's not shorter, the same, or random, that leaves.
B, they appear longer. Time intervals for moving objects appear longer to a stationary observer. This is time dilation.
Time dilation. So time really does slow down for things that are moving fast.
It's not just a perception trip, it's a real physical phenomenon. It's a consequence of the constant speed of light and the need for a consistent definition of simultaneity. The faster something moves relative to you, the more noticeable the time dilation effect becomes.
That's incredible. So our perception of time isn't absolute, it's relative to our emotion. Okay, question 8. Let's dive into some psychology. What is the concept of specious present referring to? A, the objective present. B, the time duration wherein one's perceptions are considered to be in the present. C, a false memory of the present. Or D, the feeling that time is moving faster or slower than it actually is. This is about how we experience now, that immediate moment.
Yeah, it's a really key concept in understanding our subjective experience of time.
So let's look at the options. A, the objective present is often thought of as like a point in time, a dividing line between past and future.
An infinitesimally small instant.
And C, a false memory of the present. That's more about memory distortions, not the definition of specious present itself.
Yeah.
What about option D, the feeling that time is flying by or dragging on?
That's more about our perception of the rate at which time passes, which is related but not the same as the specious present.
So B, the time duration where our perceptions are in the present. That's emphasizing that our experience of now isn't just a fleeting instant, but a small window of time.
Exactly. It's an interval, not a dimensionless point. It was first proposed by E.R. Clay in the late 19th century, and William James later developed the idea further. We integrate sensory information within this window, and it all feels like now. Think about listening to a sentence. The whole thing feels like the present, even though the beginning of the sentence was a few seconds ago.
That's a great way to put it. Our experience isn't a series of isolated moments, but a continuous flow within this now.
It's the temporal frame for our immediate conscious experience.
Really interesting stuff. Okay, question 9. Time for some biology. Which part of the brain is primarily responsible for the circadian, or daily, rhythm? A, cerebral cortex. B, cerebellum. C, basal ganglia. Or D, suprachiasmatic nuclei. So the circadian rhythm, that's our body's internal clock.
It regulates so many biological processes over a roughly 24-hour cycle. Your sleep-wake cycle, hormone release, even your body temperature, all influenced by this internal clock.
And when it gets thrown off, like with jet lag, it can really mess you up.
Oh, definitely. So let's look at the brain regions. The cerebral cortex, that's the outer layer, responsible for higher level thinking, language, reasoning. The cerebellum, that's mostly about motor control, coordination, balance. And the basal ganglia, they're involved in movement, learning, reward.
So which one acts as the master clock for our daily rhythms?
It's D, the suprachiasmatic nuclei, or SCN for short. These are tiny groups of neurons in the hypothalamus.
And what do?
They receive information about light levels directly from your eyes, so they're constantly monitoring the light-dark cycle.
So they're keeping our internal clock synchronized with the external world.
Exactly. Then they send signals to other parts of the brain and body, regulating hormones like melatonin, which affects sleep, and coordinating other biological functions throughout the day.
So these tiny clusters of neurons are basically keeping our bodies in time with the world around us.
It's a remarkable feat of biological engineering.
Okay, last question, question 10. In Western cultures, how is the mental timeline, or MTL, often spatially organized? A, past on the right, future on the left. B, past at the top, future at the bottom. C, past on the left, future on the right. Or D, no consistent spatial organization. So the mental timeline, this is about how we internally arrange events in time.
Yeah, how we mentally visualize the flow of time using a spatial dimension, like when you think about what you did last week or what's coming up next month.
And we often use spatial metaphors for time.
Hmm.
Looking forward to the future, putting the past behind us.
Absolutely. It's ingrained in our language. And research suggests it's not just metaphorical, there's often a spatial component to how we think about time. Now, it's not universal. Culture plays a big role. A, past on the right, future on the left. That's more common in cultures that read from right to left, like Arabic or Hebrew. B, past at the top, future at the bottom. That's not as common as the main mental timeline orientation in Western cultures. And D, no consistent organization. Well, research is showing that there are dominant patterns within cultures.
So that leaves option C, past on the left, future on the right.
That's the one. It's very likely influenced by our left to right reading and writing. Think about calendars, timelines, how they're usually laid out. Past on the left, moving towards the future on the right.
It's like our visual experience shapes our mental timeline.
It seems to play a role, but again, it's not universal. Those right to left reading cultures often have the opposite orientation. And some cultures, like the Yipno people of Papua New Guinea or the Pormpurauans in Australia, they use allocentric spatialization.
Allocentric spatialization.
Yeah, that they base their mental timeline on their environment or cardinal directions. So it's fascinating how diverse our conceptualization of time can be.
It's incredible. Something as simple as reading direction could influence how we map out time in our minds.
Our experiences and cultural practices really shape our thinking in some profound ways.
Well, that was the last question. We covered a lot of ground, from the atomic definition of a second to medieval monks and French revolutionaries, all the way to the psychology and neuroscience of time.
It's been a whirlwind tour.
For me, that medieval atom of time, that was a highlight. It shows how much our understanding of even the tiniest units can change. And the French trying to implement decimal time, it makes you think about how deeply rooted our systems are, even when there might be a more logical alternative.
And what I find most fascinating is just how multifaceted time is. It's studied by physicists, philosophers, historians, biologists, psychologists. It's this rich tapestry of ideas and perspectives.
And yet, it's something we all experience every single day. It's this fundamental part of reality, but it's also incredibly complex and mysterious.
Exactly.
So, as a final thought, think about how your own cultural background, your daily routines, even the way you read, might shape your own perception of time, and what other seemingly simple concepts in your life might have hidden depths waiting to be discovered. There's always more to explore, more to learn. Thanks for joining us on this deep dive into the world of time.